Hi everybody, in this video I'm going to be going over test 1 from the spring semester. So for question number 1, it says, in the diagram below of right triangle AED, we know that BC is parallel to DE. So I'm going to go ahead and just draw that into the diagram. So we have BC parallel, So we have BC is parallel to DE. Okay. So now that we know that BC is parallel to DE, we already had the congruent right angles. We also know that parallel lines cut by a transversal, here's our parallel lines, here's our transversal, create congruent corresponding angles. So we know that this angle over here should be congruent to this angle over here because they're corresponding angles. So now that we know corresponding angles are congruent, we have two pairs of congruent angles in the two triangles. In the small triangle, I'll highlight it in red, and in big triangle ADE. We have the right angle in the small triangle, the right angle in the big triangle. We have this corresponding angle in the small triangle, this corresponding angle in the large triangle. So we have that the two triangles are similar by AA. Once triangles are similar, we know that their corresponding sides are proportional. And that allows us to set up a proportion, putting corresponding parts together. So what we're going to do is we're going to look through the answer choices, and it says which statement is always true. So we're going to look for the proportion that correctly puts corresponding parts from the two triangles together. Only one is going to work because we're looking for the true statement. That means the other three must be false. So let's go one by one. Okay, answer choice number 1. We have AC. So AC is a side from the small red triangle. So I'm going to write here small. And looking at the bottom over here, we have BC. And BC is another side from the small red triangle. So in order for this proportion to check out and put the corresponding parts together, over here should be the side from the big triangle corresponding to AC. And here should be the side from the big triangle corresponding to BC. If I take a look at AC, the side corresponding to AC on the big triangle is AE. So in order for this to be true, this should say AE. And the side corresponding to BC on the big triangle is DE. So in order for this to be true, this should say DE. So this is not correct. It is an incorrect proportion. Let me take a look at answer choice number 2. We have AB, and AB is from the small triangle once again. And we have AD. AD is the corresponding side to AB from the big triangle. So we have side from small triangle, and we have corresponding side from big triangle. In order for this proportion to check out and be accurate, we should have another side from small triangle as the numerator, the corresponding side to it from big triangle as the denominator. So BC, we do have a side from small triangle, so that's good so far. Now let's see if the denominator is the corresponding side from big triangle. So BC, the corresponding side in the big triangle is DE. So that is the corresponding side from big triangle. That checks out. That's the correct answer. We can look through the other two choices to see why they're wrong. BC is a side from small triangle. CE is like not even a side from any of the triangles, so that's not good. Goodbye that answer choice. Okay, DE is a side from big triangle. BC is the corresponding side from small triangle. So in order for this to check out, we should have another side from big triangle over the corresponding side to it from small triangle. DB is like not even a side from any of the triangles. It's not a side of the big triangle, and it's not a side of the small triangle. So that's not the correct answer choice either. Number 2. In the diagram below, AD intersects DE at C, and AB is parallel to DE. We have vertical angles here, and we also have congruent alternate interior angles since we have parallel lines cut by a transversal. Now we can see that the two triangles in this diagram are similar by AA, so that means the corresponding sides are proportional. So we can set up a proportion involving the corresponding sides. We know that CD is 6.6. We know that DE is 3.4. We know that CE is 4.2. And we know that BC is 5.25. And we're looking for the length of AC to the nearest hundredth of a centimeter. So let's set up a proportion. So in order to set up my proportion, I'll just start with, I guess, a side from big triangle, and I'll put it over the corresponding side to it from small triangle. So I'm going to start with 5.25 from the big triangle, and I'll put it over the corresponding side to it from the small triangle, which is 4.2. And to complete my proportion, I'll take another side from big triangle, so X, that's what we're trying to find, that's AC. And I'll take the corresponding side to it from the small triangle, which is 6.6. Now that I have my proportion, and once again, not the only way to set up a proportion, but definitely a valid one, I can cross multiply. 5.25 times 6.6 is 34.65 on my calculator, and that's equal to 4.2 times X. If you divide both sides by 4.2, you should get 8.25. Scalene triangle ABC is similar to triangle DEF. Which statement is false? Okay, let me draw some diagrams. So if this is A, B, C, then over here, this is D, E, F. They're similar triangles. Remember, corresponding angles are congruent and the corresponding sides are proportional. So let's go choice by choice. So choice number 1, AB, is this side over here. And the ratio includes BC. So that's side from small triangle, side from small triangle. So the other side of the proportion, DE, should correspond to AB and should be from the big triangle. EF should be from the big triangle and should correspond to BC. So let's check it out. DE is from the other triangle and does correspond to AB, so that's good so far. EF is from the other triangle and does correspond to BC, so that's also good. So that's a correct choice. 2. AC, that's from this triangle over here, and DF, that is the corresponding side to AC from the other triangle, so that's good so far. Here we should have another side from the left-hand triangle and the corresponding side to it from the right-hand triangle. So we have BC, and that does correspond to EF, so that's all good as well. 3. Angle ACB, so that's this angle over here, is congruent to angle DFE. Well, that's true. These are corresponding angles in the similar triangles, so they are congruent to each other. It's a true statement. And finally, angle ABC is congruent to angle EDF. Now, this is the false one. These angles are not in the same spots on the two triangles. They're not corresponding angles, so I don't know that they're congruent. So that's the statement that is false. The sides of a triangle are 8, 12, and 15. The longest side of a similar triangle is 18. What is the ratio of the perimeter of the smaller triangle to the perimeter of the larger triangle? Well, let's see. Let's see what the scale factor is, since corresponding sides are proportional in similar triangles. If I do 18 divided by 15, I get 1.2, and I'll put that over here. 18 over 15 is 1.2, and that's the scale factor here. So that tells us to get from each side of the smaller triangle, we're going to multiply by 1.2 to get the corresponding part from the larger triangle. So I'm going to do 8 times 1.2, and that gives me the side of this triangle, which is 9.6. And I'm going to also do 12 times 1.2. And that gives me the corresponding side from this triangle, which is 14.4. Okay, I can add up to find the perimeter. 8 plus 12 plus 15. Oops, my calculator messed up. 8 plus 12 plus 15. And I got 35 as the perimeter. And I can add up the sides here. I have 18 plus 9.6 plus 14.4, and I get 42. And if I divide 42 by 35 as expected, I get 1.2. So basically, we didn't even have to find the perimeters. Once we found the scale factor, that was the answer, because the perimeters of similar triangles are in the same ratio as the sides. Since all the sides are proportional by the same scale factor, the perimeter has to be proportional by that same scale factor as well. So once we found that scale factor, we already had our answer. We just need to see which of the answer choices means 1.2. So 2 to 3 ratio, that's the same thing as 2 over 3, because we can rewrite with instead of a colon as a fraction. 2 over 3 in my calculator is not 1.2. Okay, this is 4 over 9. In my calculator, 4 over 9 is not 1.2. Okay, this one over here is 5 over 6. In my calculator, 5 over 6. So on my calculator, 5 over 6 is not 1.2, but if we do it the reverse way, 6 over 5, it is. So I actually misread the question a little bit, because it specifically says the ratio of the smaller triangle to the larger triangle. So since for the scale factor, I divided bigger over smaller, I was actually doing larger triangle to smaller triangle. But if we're doing smaller triangle to larger triangle, we should switch these to smaller over larger. We can also do it with the perimeters. Instead of doing the 42 over 35 like we did to get the 1.2, we should do the smaller over the larger, because we want the ratio of smaller to larger. And on my calculator, when I do 35 over 42, I get 0.833333 repeating. So I'm going to write here 0.83 repeating so that we can keep that in mind. So I'm just going to go through the answer choices and try them out once again in my calculator. So 2 over 3, that's 0.667. So that's not 0.83. Okay, 4 over 9. On my calculator, that's 0.44444 repeating. So that's not what we're looking for here. 5 over 6. If I put it into my calculator, it is 0.833333 repeating. So that's the answer choice we're looking for. The last one, if I wanted to try it out, 25 over 36 in my calculator, that's 0.6944444. So that's not what we're looking for either. The accompanying diagram shows part of the architectural plans for a structural support of a building. Plan is a rectangle, and AS is perpendicular to LN. So since AS is perpendicular to LN, oops, I'm just going to put in my right angles here. And since we know that plan is a rectangle, I know that there are 90-degree angles in the corners. I can put that in all of the corners. I can put it here. And I think that one makes things a bit clearer, because now we can see that we have a big right triangle with an altitude drawn to its hypotenuse. So we know that that's a situation where we can use the right triangle altitude theorem. And it's asking which equation can be used to find AS. AS is the altitude drawn to the hypotenuse of the big right triangle LAN. So we're going to be using the altitude rule. Remember that the altitude rule says that the altitude, which is AS here, or X, I'll just write AS because AS is how the answer choices are listed. So the altitude AS is the mean proportional between each part of the hypotenuse. So between this part of the hypotenuse LS and between this part of the hypotenuse SN. And that's answer choice number 1. That's just using the altitude rule of the right triangle altitude theorem. Okay. This question is pretty simple. The most difficult part was understanding the question. Let me just make it a bit smaller so that we can see the whole thing at one time. Maybe if I view it out, it would be a little bit better. There we go. That's a little better. Okay. The accompanying diagram shows a section of the city of Tacoma. High Road, State Street, and Main Street are parallel and 5 miles apart. So the 5 is already here, and I can just put in that all the roads are parallel to each other. The Ridge Road is perpendicular to the 3 parallel streets. So here's Ridge Road, and it's perpendicular to each of the 3 streets. Okay. I'm just going to leave this one, because if I leave this right angle over here, we can clearly see that we have a right triangle, and that's going to be helpful to us, having a right triangle here. The distance between the intersection of Ridge Road and State Street, so Ridge Road and State Street, they intersect. Here's Ridge Road, here's State Street, and they meet right over here. This is the intersection of Ridge Road and State Street. And where the railroad tracks cross State Street is 12 miles. Here's the railroad tracks, here's State Street. So here's where the railroad tracks cross State Street. So this length over here is 12. What is the distance between the intersection of Ridge Road and Main Street? So here's Ridge Road, here's Main Street, here's where they intersect, and where the railroad tracks cross Main Street. Here's the railroad tracks, here's Main Street, here's where the railroad tracks cross Main Street. So this is what we're looking for, this distance here. Since Ridge Road was parallel to each of the other streets, I'm going to put this right angle back, was perpendicular to each of the other streets. I'm going to put this right angle back here. That way we can see that small triangle here, and I'll outline the small triangle in red, is similar to the big triangle, and I'll outline the big triangle in black so you can see it. They each have a right angle, that's a congruent angle, and they share this angle over here by reflexive property. So we do have similar triangles, but means the corresponding sides are proportional. So we can set up a proportion in order to find the missing side length of the big triangle. So let's think about what we do know. In the small triangle, I know that this side over here is 5. So that's from small triangle. And I know the corresponding side from big triangle is 5 plus 5, which is 10. So that's from big triangle. I need another side from small triangle. So the only other side I have is 12 from the small triangle. And the corresponding side to it from the big triangle is the side that we're trying to find, labeled x. If I cross multiply, we have 5x is equal to 10 times 12 is 120. And if we divide by 5 by both sides, 120 divided by 5 is 24. So we have x is equal to 24. Let me write that in. You might have recognized that you didn't even need to set up a proportion. If small side is 5 and big side is 10, scale factor is 2, double 12 is 24. And you could have been done with the problem already. Okay. Number 7. 4 streets in a town are illustrated in the accompanying diagram. If the distance on Poplar Street from F, P, is 12 miles, and the distance on Maple Street from E to M is 10 miles, find the distance on Maple Street from M to P. So that's what we're finding. So we have a big right triangle with an altitude drawn to its hypotenuse. So this is a right triangle altitude question. We don't have the altitude and we're not trying to find it. We do have information about one of the legs of the big right triangle. So we're going to be using the leg rule here. Remember that the leg rule says that the leg is the mean proportional between the whole hypotenuse. The whole hypotenuse is 10 plus x, this and this part together, and the part of the hypotenuse directly below that leg, which is also called the leg's projection on the hypotenuse. All I need to do now is cross multiply and solve for x. That's 10x plus x squared is equal to 144. We have a quadratic equation. The largest exponent is 2. So I want to get it equal to 0. And I'm going to reorder it a bit. I'm going to put the x squared first, and then the 10x. And I'm going to subtract 144 from both sides to get my equation equal to 0. From here, I'm solving a quadratic equation by factoring. So I'm going to think about what my two factors are going to be. They need to multiply to give us negative 144 and add to give us 10. So you can play around with that for a bit, and if you want to pause the video to try to figure out what those factors would be, go ahead and do it. Those factors turn out to be 8 and 18. Since we want the sum to be positive, the larger number 18 should be positive, and the smaller number 8 should be negative, so that when we multiply them, we get a negative 144. 18 times negative 8 is negative 144. 18 plus negative 8 is positive 10, just like we need. So if we solve this quadratic equation, x plus 18, if we subtract 18 on both sides, we have x is equal to negative 18. Remember, you change the signs. X minus 8. When we solve that equation, we have x is equal to 8. Since we're working with a real-life situation with triangles, it doesn't make sense that a side length would be negative. So we always reject the negative in geometry, and we go with the positive value. So the x value that we're looking for, which represents the distance from M to P, would be 8. In triangle CED, as shown below, points A and B are located on CE and ED respectively. Line segment AB is drawn such that AE is 3.75, AC is 5, EB is 4.5, and BD is 6. Explain why AB is parallel to CD. So I see a small triangle here and a big triangle. So let's make a statement about these two triangles first. I see that they share angle E by the reflexive property. And this whole side is, what is that, 8.75. And this whole side is 10.5. Let's figure out what the scale factors of the corresponding sides are to see if they're proportional. So 8.75 over 3.75 on my calculator, that gives me 2.333 repeating. And if I do 10.5 over the corresponding side from the small triangle, 4.5 in my calculator, let me see what that gives me. That gives me 2.333 repeating. So I can start writing my explanation. I'm going to write triangle AEB and triangle CED are similar by side angle side. The corresponding sides are proportional by the same scale factor, and our work above shows that. And the angle in between the proportional sides, and that's angle E, that's the one in between the proportional sides, is shared between the two triangles. You can also say is congruent to itself by the reflexive property. Now that we know the triangles are similar, we know that the corresponding angles are congruent, because anytime we have similar triangles, corresponding angles are congruent. So that means this angle and this angle are congruent. This angle and this angle are congruent. These are the corresponding angles in the two triangles. And guess what, guys? If corresponding angles are congruent, that makes the lines forming them parallel. Remember, just like having congruent alternate interior angles is one way to show that lines are parallel, having congruent corresponding angles is another way to show that lines are parallel. So I'm going to add this into the explanation. Okay, since similar triangles have congruent corresponding angles, angle EAB is congruent to angle ECD, and angle EBA is congruent to angle EDC. If corresponding angles are congruent, then the lines forming them are parallel. And I'll just finish it up, making AB parallel to CD. And there we go. Next, we have the proof. This proof was exactly from the group work that we did from lesson 1 on proving triangle similar. The very first lesson we did with the chart paper, and then we corrected each other's work, and each group got assigned a question, and we put it up on chart paper. The answer key to that's posted on Google Classroom. It's under Unit 1 classwork. If you take a look at that, it's called Proof Activity Answer Key. You'll see that this question was exactly there. So a lot of things that are on our test are taken directly from like classwork or homework. Okay, so in right triangle ABC, angle C is the right angle. So I'm going to put that in here. And CD is perpendicular to AB. I don't know which right angle is going to be important to me yet because I don't know which two triangles are proving similar. Luckily, in part A, it tells me exactly which two triangles we need to prove similar. Triangle BCA, so that's the whole big triangle, and triangle CDA. So that's this triangle over here. So this angle is not going to help me because this angle that I just erased was not in triangle CDA, the red one, and it's not in the big black triangle either. Already, from just our given information and drawing in those right angles, we already have a pair of congruent angles in the big triangle and the small red one. We have the congruent right angles. And if you take a look, angle A is an angle in the small red triangle. It's also an angle in the big black triangle. So angle A is congruent to itself by reflexive property. And there we have angle, angle. So let me start writing this proof. And it's really, really straightforward. So number 1, right triangle ABC. I did not give myself a lot of room. Angle C is a right angle. CD is perpendicular to AB. And that is all given information. Step number 2. Angle CDA, that's this angle right here, is a right angle. We knew that from our givens because we had perpendicular lines, and we know that perpendicular lines form right angles. We want to say that the right angle in the big triangle and the right angle in the small triangle are congruent to each other, so we can use it for AA. So for my next step, I want to say that angle C, which we knew was the right angle from my givens, is congruent to right angle CDA, which proved as a right angle in the previous step. And our reason for that can be all right angles are congruent. From there, I need to mention the other pair of angles that I'm using for AA, and that's angle A being congruent to itself. And that is due to the reflective property or postulate. Now we have AA in the big triangle and the small triangle. So we can prove part A, we can prove that triangle BCA is similar to triangle CDA, and that's by AA. Even if you had no clue like how you were going to get the angles, we've talked about in class many times how most commonly in two-column proofs, it's always going to be AA to prove the triangle similar. So you could have filled in this step even if you didn't know what came in between. Also, we all know that perpendicular lines form right angles. So I think everyone could have figured out that there was a right angle here and here as well and gotten at least something in the proof. Let's continue because now we have part B. And part B is actually really straightforward. We need to prove a product involving the corresponding sides from the small red triangle and the big black triangle that we just proved similar. Before we can prove a product, we need to prove a proportion because we need to be able to cross multiply the proportion to make the product. So in order to make a proportion, a really easy way is you can just divide the extremes. So AD and AC are the extremes. So I can just divide them. AD over AC is equal to, and then I can divide the means together. DC and CB are the means. And just to double check it, if I cross multiply, AD times CB, that's what we need on the left. DC times AC, that's what we need on the right. And the reason for proving a proportion is the same reason every single time. So if you don't know this reason, that means you didn't study your notes. If triangles are similar, then their corresponding sides are in proportion or are proportional. Are in proportion. I don't know what I'm writing here. There we go. And finally, to finish it up, it's one more step to get from a proportion to a product because you just cross multiply the proportion to get the product. So my last step is the product that we're trying to prove. AD times CB is equal to DC times AC, and the reason's the same every single time. So if you didn't get the reason for this very last step, probably then study your notes from class. The reason is in a proportion, the product of the means equals the product of the extremes. And there we have it. That's the whole proof. We did part A and part B all in one. I do want to show you guys how to do the extra credit because I feel like a lot of people tried it but didn't really know how to approach it. So I'm just going to make like a random triangle and I don't know, I'll just make it a really easy kind of triangle. I'll just make an equilateral triangle. Let me get my compass out, and this is the line segment I'm going to use. So just to make my like random triangle, I'm going to just, oops, my compass is moving everywhere. I'm going to put my compass on one endpoint, and I'm just going to open up to measure how long the line segment is as accurately as I can, and I'll just make an arc to indicate that I measured it. And I'll just make a small arc up here, and using the same length, I can go over to the other endpoint. Sorry, my compass is like flailing around here. It's very hard to do on the computer. Can make another arc here, and that's where I should draw my line segment through. So I just constructed this equilateral triangle, and all three sides have the same length as the line segment I started with, but it wasn't really specific, the question, whether you had to construct the triangles or whether you could have drawn one triangle and the second one just had to be constructed to be double the length. That wasn't clear, but we're going to do it with fully constructing the triangles. So I need a starting point for my next triangle, so I'm just going to make a point here, and that can be my starting point. And since I didn't change my compass length, I didn't change how far it was open, the amount of distance that it's open to still represents the length of each side of this triangle over here. So we want to double it because we want a scale factor of 2. So I'm just going to make an arc, and I'm indicating that that is one side of the triangle, but I want to double that. So then I'm going to move my compass over here, and I'm going to put the length again. And that should be double. Should be exactly double. Starting at the point, I'm just going to draw a line segment. Sorry about that. And now I have a side of the triangle that's exactly double. I want to make my other sides the same length because I made an equilateral triangle to begin with. And I want all the sides of my new triangle to have a scale factor of 2 from the original. So now that we've accurately measured, I can just open up my compass all that way. Let me make an arc here. On the other endpoint, let me make another arc. Trying to not mess this up. There we go. Good thing I moved the compass when I was done anyway. And then I'll just draw a line segment to my intersection points. And now I have a triangle whose sides are exactly double the side lengths of the original, because once again, it's an equilateral triangle. So in order to get full credit for this construction, a lot of people constructed an equilateral triangle, but in order to get full credit for this construction, I had to see that you measured the original length and that you doubled it. So my 2 arcs here showed that I actually doubled the length of my original triangle. So that's why a lot of people didn't get the credit. So I just wanted to show you guys a way to do it. So that way, if you were interested, now you know, and you can try it on your own.